Okay, so we've established that what it takes to be an eigenvector is that when you multiply a matrix by that vector, all you get out is a scalar multiple of the same vector. So I can write that kind of as an equation. I'll say that if I take a matrix A and multiply it on the right by a vector x, if I get just a scalar multiple of the same vector x out of that multiplication, then x is an eigenvector. What we're going to do in this video is figure out how to find this number right here. What is that scalar? What is the scalar that results from this multiplication? You know that x is equal to x. We'll be given some matrix A, but how do we determine what lambda is, what that scalar is? Well, if I take this, this equation and I subtract, let's see, I'll do it very formally here. I'll start with this equation, and I'll subtract from both sides the quantity lambda x. When I do that, I get a times x minus lambda times x equals 0. Now that is basic matrix arithmetic. That's a vector, it's a zero vector. Basic matrix arithmetic. But we haven't been doing that kind of arithmetic for very long, so I wanted to sort of spell it out for you here. And something to note, what I've done here is matrix subtraction. I have a matrix here minus another matrix, and I can technically get away with that, except that here these matrices are potentially different sizes. Remember that matrix addition and subtraction only works if your matrices are of the same dimension. So I need to make sure before I do this, before I subtract this column matrix from this other matrix, that they have the same dimension, and they may not. So I'm actually going to erase some of this and take a step back here. All I'm going to do is rewrite my second line as rewrite my first line as ax times lambda x, but I'm going to stick an identity matrix in there. Now what I have is the scalar lambda times an identity matrix. So if we're in n equals 2, so a 2 by 2 matrix, then I would have some scalar times 1, 0, 0, 1. When I scale 1, 0, 0, 1 by, say, n, I get n0, 0, n. Now when I do this multiplication, I'm going to get the same result as I get here. I'm going to have the same dimensions as I have back here. So I can do now matrix addition and subtraction by subtracting lambda I x from both sides. This addition of the identity matrix is actually going to serve another purpose as well. So it's actually quite useful to have in there. So now what I have is A times the vector x minus lambda times the appropriately sized identity matrix times the column vector, or the column matrix or vector x, is equal to 0. These two cancel each other out. And I can unmultiply from the right the vector x. So now I'm going to write this as a minus lambda times the identity times the vector x on the right equals 0. So now what I have is a matrix equation here, right? I have some matrix, a matrix minus another matrix, times a vector equals a vector. I suppose I should put my vector mark over here so this is not clear. Otherwise, that's the 0 vector. So now, just algebraically speaking, there are two different ways in which this equation can be true. One is that x can be the 0 vector. Okay, if x is equal to the 0 vector, then it wouldn't matter what any of this was. In other words, if x is the 0 vector, lambda could be anything. What we're really trying to do here is find lambda, right? If x is the 0 vector, then lambda can be anything. Lambda, let's see, how do I want to write this? Then I'll say lambda is an element of a set of real numbers. It can be any number, and that's not very helpful. Remember that what we're trying to do is find this number, and what we've discovered here is that under this particular condition, it could be anything. So we need to find an alternative strategy. We'll make the argument here that we're going to assume, because of this property, because of this snafu, if you will, we're going to assume that x is not the 0 vector, that this situation that we're working with here We're not interested in the trivial aspect, the trivial situation. So we're going to assume that x is not the zero vector. In fact, when we define an eigenvector, we say that it is a non-zero vector. And this is part of the reason why that piece of the definition is so important. Now, if x is not zero, let me get a highlighter here. If x is equal to zero, then the whole thing is zero, right? By the zero product property, either one of the factors or the other one must be zero for the right-hand side to be zero. Well, we just said that we don't want x to be zero, so that means that we're left with a minus lambda times the appropriately sized identity matrix equals the zero vector. Well, because of our inclusion of the identity matrix up here, we know that A and lambda I, this is a scaled matrix, we know they're the same dimension. So we can get away with this subtraction, and we want the result of that subtraction to be zero in order to figure out what lambda is. The invertible matrix theorem from, way back tells us that this equation has a non-trivial solution, right? The answer is not just zero, if and only if the determinant of the left-hand side, so I'm going to write determinant of A minus lambda I, if that determinant is zero. We're going to do an example here in a minute, so you'll see what the determinant of a matrix, a subtracted pair of matrices looks like in just a second with this lambda in it. But I want to point out, I want to highlight the fact that this equation is what we call the characteristic equation. And it is the characteristic equation for the matrix A. Another matrix, let's say B, that's the same dimensions as A, is going to have a different characteristic equation. It'll still have A lambda. We don't know what lambda will be in that case. It'll still have the same dimension identity matrix because A and B are the same dimensions. The identity matrices that we use in this equation will also need to be the same dimensions. But A and B are different matrices. So what we have here is the characteristic equation for matrix A, and in another situation we would have the characteristic equation for matrix B, a different matrix. So I'm going to highlight this in blue, I guess, because that is an important definition. We've got a couple of other new vocabulary words that we'll get to in just a minute. Let's take a minute now, though, and actually work through an example. I've moved all that new stuff down to the bottom left-hand corner here so that we have a little bit more room on the same screen. I'm going to use a matrix A that is -2, 0, -2, 4. And the first thing I'm going to do here is find the eigenvalues of this matrix. There may be more than one, and in fact there are likely to be more than one, and we'll talk about why that is in just a minute. And in order to do that, we don't need our eigenvector, right? If we look back at this equation here, the eigenvector, potential eigenvector, is nowhere in here. All we have here is A, which is this matrix here, and lambda times I. And I here is going to have the same dimensions as A, so it'll be 1, 0, 0, 1. And when I multiply lambda by I, lambda is just a scalar, I get the matrix lambda, whoops, when I write my lambdas, I write them, my hand wants to do the same thing as I do when I write an X. So I get this matrix. That's my lambda I. So A minus lambda I is the matrix -2, 0, -2, 4, minus the matrix lambda 0, 0, lambda. That gives me, just matrix subtraction now, -2 minus lambda, that is this entry minus this entry, And then I'll do that for each of these others. Okay, so I'm going to get 0 minus 0, negative 2 minus 0, and 4 minus lambda. 0 minus 0 goes here. Negative 2 minus 0 goes here. And 4 minus lambda goes here. And that is a new 2 by 2 matrix because I have subtracted a 2 by 2 matrix from another 2 by 2 matrix. And what I want to do now is take the determinant of that. The determinant of A minus lambda I is the product of these two entries here. I'll just write it out. Negative 2 minus lambda times 4 minus lambda minus the product of these two entries. And in this case, we have a 0 here, so we're left. We just write it as minus 0. I'm not even going to write the minus. Let's get rid of that. Save some space. Well, that's going to be a quadratic equation in lambda, right? The lambda is going to be my variable here. Negative 2 times 4 is negative 8. That's this one. I have negative 2 times negative lambda, so I have plus 2 lambda. Negative lambda times 4 minus 4 lambda. And then negative lambda times negative lambda is minus lambda squared, which simplifies to lambda squared minus 2 lambda minus 8. And that, I believe, factors. I'm running out of room. I'll write that on my gravestone. I think she ran out of room. Okay, 1 times 8 is 8. 2 times 4 and 2 minus 4. Okay, so I have a 2 and a 4. And I have a negative 2, so that's going to be negative, and that's going to be positive. So lambda equals either negative 2 or, put a comma there, or positive 4. This is just an equation, right? This is just a quadratic equation where lambda is the variable. And all I've done is solve that for lambda, right? I got that quadratic equation by taking the determinant of this matrix. This matrix was the result of subtracting two matrices. So you have to set this up. You have to know what your dimensions are so you can find the right I. You scale it through by lambda. You subtract them. You create one matrix, that's the result of that subtraction. Then you take the determinant of that, which gives you this quadratic. You solve the quadratic, and you have your values for lambda. So if you're looking for the eigenvalues, which are lambda in this equation, not the eigenvectors, the eigenvalues, then this is how you do it. You'll need to figure out what your identity matrix is, scale it, subtract, find the determinant of the results, solve the resultant quadratic. Those are my two eigenvalues for this equation. It's interesting to note that there are two, and there are two dimensions here. This is a 2 by 2 matrix. Can you find an eigenvalue, or an eigenvector for that matter, for a matrix that is not a square matrix? In other words, could you find an eigenvalue or an eigenvector for a matrix that was a 2 by 3 or a 3 by 2? Is that possible? Well, the answer to that question is no. Let's see if we have, I'm just going to do this in this space in the middle here, which is really cheating, and I apologize, but otherwise out of room. If I had a matrix like, I'll just go with 1, 2, 3, 4, 5, 6, that's a 3 by 2, and I multiplied it by some vector AB, the result would be 1 times A plus 2 times B, 3 times A plus 4 times B, 5A plus 6B, and that is a 3 by 1 matrix. There is no way for this matrix, for this 3 by 1 matrix or a vector, right? Once I add these numbers together, this is going to be a single numerical value, as is this one. I've got a column matrix here that is 2 by 1, and this one is 3 by 1. This cannot be a scalar multiple of this if they're not even the same dimension. So in order to be able to find an eigenvector or an eigenvalue for a matrix, the matrix you're working with has to be a square matrix. Otherwise, you won't be able to do this work. So we're only working with n by n matrices. And with this n by n matrix, our dimensions were 2 by 2, and so we could say n equals 2. Just going to get rid of this. And you'll notice that we have 2 eigenvalues. An interesting observation. We'll see as we go on whether this is a one-off, coincidental, or if it actually holds for every case. Just a little bit more vocabulary here. This equation that we came up with that we needed to solve is called the characteristic polynomial. Right, that's because it comes from the characteristic equation. And the collection of all possible eigenvalues, I'm going to write them in this form here. I have -2, 4. This is called the spectrum of the characteristic equation, and you will also sometimes see it denoted as lambda A because it's the spectrum of eigenvalues for the matrix A, right? These eigenvalues only work for this matrix. I mean, they may appear as eigenvalues for another matrix, but for this particular situation, first of all, these are the only 2 eigenvalues that there are, and they won't necessarily be the same 2 for some other matrix. Of course, there are going to be some other matrices out there for which these are the same 2 eigenvalues, but they're unique to this matrix, right? So we say that this is the spectrum of A, and sometimes we denote it using, oh, that's messy, using this notation here. That's a lambda, not an x. I'm not going to take the time to do it here, but I want to point out that you can also find the eigenvectors, the eigenvalues for a 3x3 matrix or a 10x10 matrix. In order to find the eigenvalues, you're going to need to be able to take the determinant of a 3x3 matrix, because we would have a 3x3 matrix we were calling A. Our identity matrix would be 3x3. When we scaled it, we'd have a 3x3. When we subtracted, we'd have a 3x3, and then we'd need to take the determinant of that 3x3 matrix. So that's also possible, and I know you know how to take the determinant of a 3x3 matrix. So I'm not going to do it in this video, but if I get a chance, I'll make another video just with that, an example of a 3x3, the eigenvalues for a 3x3 matrix. But just as at the end here, I want you to be aware that that is a possibility. In fact, you could find the eigenvalues for a 12x12 matrix. But that's, above and beyond the call of duty, and mostly would be done on a calculator anyway. So